This video introduces a select case analysis of sustainable architecture concept for Souq al-Jum'ah in Sharjah, UAE. The main contents of a project is introduce the main objectives, the project definition, the geographic location of Sharjah city with climate analysis and site analysis, introduce the case study description, methodology and concept design analysis, dynamic thermal simulation by AS and InVimit analysis, propose 3D modeling of the proposed building.
The project purposes. First of all, to understanding the impact of adopting traditional vernacular architecture features in contemporary buildings in the United Arab Emirates. Second, to establish the theoretical background of various aspects that affect the development of as-Souq buildings and its future directions. Third, to set up a 3D modeling of the existing building, case study of Souq al-Jum'ah, and validate the available building drawings and data. Fourth, to examine proposed 4 sustainable strategies for enhancing the building energy performance. Finally, comparing and verifying the final results and choosing the optimal energy efficient solutions.
Let us describe the development of a traditional souq in the UAE from 60s to 2000s. Prior to the oil plume era, architecture prominent feature distinguished by the walkable souq narrow alley way to defining the shopping streets. In the 1960s, modernist aspiration. A shift towards heavy prefabricated and modular construction started. In the 1980s, the launch of the first shopping mall, Al Ghurair Center in Dubai, a huge shift from local traditional architecture souq to the westernized large shopping mall. Hedonistic modernism by the 1990s, a competition among developers and architects diverged from its origin, seeking the bigger, taller, and the faster. The economic crisis hit in 2008. The market started seeking to cultural, environmental, and sustainable architecture. Al-Souq is the Arabic word for market. The traditional Emirati souq is the spirit of a place, is the memory of the place, is the most connected to the people. Al-Souq is for commercial exchange and is for social networking forum. This is an example of Sharjah Souq, Souq al-Arasa. Souq al-Arasa is courtyard souq, is one of the oldest marketplaces in the UAE. Let us mention the most common traditional materials used in Emiratis construction buildings based on local. The first one is coral stone, which has a strong thermal insulation due to its cellular composition and lightweight. Coral stone is bonded with sand lime mortar. Palm fronds is another common material about 500 years ago. The shelter's frame was made out of mangrove poles and split palm trunk, while palm stems were tied together to make panels to construct the walls. Al-Arish house using palm tree as a building material. The main common heritage traditional features such as the wind tower, which is called Barjil. Barjil is one of the prominent architecture elements in the UAE. The main function of Barjil is to catch the wind and cool the indoors, while courtyard is for privacy and improved thermal environments. Mashrabiya is another architecture feature to manage the natural light and avoid glaring. Shading devices cover the main walkway to create shape of the space and filtering light into the space. Narrow passageways is called Sika to define shopping streets.
Geographic location. The site was chosen in the Emirate of Sharjah, specifically in the Meleha area in the central region, which is approximately 70 km from Dubai, 60 km from Sharjah, and 45 km from Fujairah. It can be reached by using the Emirates Road, passing through Sharjah Kalba Street toward the eastern region.
Related to the site analysis, Souq al-Jum'ah is located to the southeast of Meleha Road and nearby to the Circle Road to Fujairah city.
Climate analysis. The temperature range in the hot season runs from May to September, with an average daily high temperature above 37 degrees Celsius. The warmest month in August with 43 degrees Celsius, while the cold season runs from December through March with maximum daily temperature average less than 27 degrees Celsius. January is the coolest month with 24 degrees Celsius. Monthly diurnal averages. The majority of dry bulb temperature are above the comfort level. This indicates that the weather is mostly hot. The direct normal radiation average is around 800 watt-hour per square meter from May to September. The location is exposed to a high level of solar radiation. Relative humidity. Sharjah experiences absolute variation in the relative humidity over the year, about 69% during January and December. May is the least humid month, about 51%.
3D sun bath of the base case showed summer solstice during the 21 June. The sun angle altitude is about 88, which is high, while the winter solstice angle solar altitude is about 41 degree. The prevalent wind blowing from the west direction with average speed about 3 meters per second, while the march is represent the highest speed with 4 meters per second. Let us describe the existing building layout. Al-Souq is sitting on rectangular plot designed as a traditional souq with linear U-shaped plan. It's divided into 5 blocks. Each block has 9 typical shops arrayed linear, and each shop dimension 6 by 10 meters, while the corner blocks represent the prayer rooms, administration rooms, and services. Our study selected the Block A in order to save the simulation runtime and achieved improved alternatives using showbox concept to enhance design development stage. Form development based on redesigning the proposal form to create a new access pathway starting from each cluster. Adjusting the existing building based on developed form, starting with zoning by dividing Block A into clusters and separated between the 3 stores is placement. Following by circulation by creating a centric access for visitors in certain direction. Finally, the vision to be considered and having a viewing. The conceptual form development demonstrates in sequence starting with linear spatial typology, clustering and displacement, rotate to create what we call central courtyard typology, creating a private enclosure and create a private semi-court in each cluster. Finally, creating a new building layout shape. These videos show a 3D model of sun bath during summer solstice and winter solstice for the new building layout form. Recommended design strategy for building energy conservation that employ in the existing building is starting by modifying the base case. Strategy A, adjusting the building orientation. Strategy B, integrated various scenarios of shading devices. Strategy C, scenarios assigning for different glazing properties. Finally, build 3 scenarios of green roof to meet the study targets. The dynamic thermal simulation by IES used a profile database tool in IES to create a certain daily and weekly profile of the study modeling. To start the dynamic thermal simulation via Apache, we compare the actual electricity bill. The reference case selected is a shop 45. To establish a credibility, the overall of the simulation result of the reference case are calibrated with the monthly electricity bills. Let us start with energy modeling to show the final result of the total annual cooling loads and electricity consumption for each scenario. The total annual cooling loads and electricity consumption of the base case investigated by Apache tool refer to the existing building under the real condition. There is a significant consumption in cooling loads during August and July. The base case consumed 133.4 megawatt of the total annual electricity and 228.9 megawatt per hour of the total annual cooling loads. The final results of dynamic thermal simulation will present the following strategy. Strategy A, building orientation. B, integrated shading devices. C, glazing properties. And D, green roof. Strategy A is based on adjusting the building's orientation towards the major 8 different directions, considering that the base case was inclined at the southeast around 207 degrees. The southeast direction of the building achieved the highest reading energy consumption, while the west direction achieved the ideal building orientation. The highest loads are recorded in the northeast direction, accounting for 136 megawatt of total annual electricity, while the west direction achieved the lowest reading, reached to 126 megawatt per hour. Strategy B adjusted each module by integrating different feature architectural of shading devices. We selected a brise soleil, which is an architectural feature, a sunshade structure. A horizontal projection extends from the sun side facade of the building to prevent overheating during hot time. The main function is to avoid high-angle summer sun falling. The selected shade device scenarios as following. Scenario 1, brise soleil overhang with horizontal louvers. Scenario 2 is overhang with surrounding shading. Scenario 3 is overhang with vertical louvers. The first scenario is referred to Scenario 0, which is the new building layout shape of a souk without shade. The total annual electricity consumption is 126.8 megawatt per hour, while the total annual cooling load is 215.93 megawatt per hour. Scenario 1, which extends the horizontal projection overhang, improves the total energy consumption of the building in comparison to the base case, slightly decreasing in total annual cooling loads in comparison to the previous case. The total annual electricity consumption is 124, while the cooling loads is 210.3 megawatt per hour. Scenario 2, integrated overhang with surrounded shade, achieved better energy performance than Scenario 2. The total annual electricity consumption is 123.9 megawatt per hour, while total cooling loads is 209.9 megawatt per hour. The last scenario of integrated shading devices is Scenario 3. Built overhang with vertical louvers achieved better performance than the previous scenario. The total annual electricity consumption is 123 megawatt per hour, while the cooling load is 208 megawatt per hour. Strategy C, based on replacing the current glazed facade by installing 3 different glaze types, which has different thermal properties. The main tested glazing options as following. G1 refers to lowy coating double pane. The next is G2, refers to insulating glass unit double pane spectral selective glass. The third one is G3, triple glass pane. The optical and thermal properties for each glazing type. The solar heat gain coefficient of G1 is 0.139, while the glazing 2 is 0.160, while the solar heat gain coefficient of G3 is 0.089. The total annual electricity consumption for each glazing type as following. Glazing type G1 achieved the highest annual electricity consumption to 121.2 megawatt per hour, following by G2 accounting 119.8 megawatt hour. In contrast, the G3 is achieved the highest reduction in the total electricity consumption to reach 117.4 megawatt per hour. Strategy D, based on enhancing the thermal insulation of roof by assigning 3 different scenarios of a green roof. The difference in between them based on the thickness of a growing substrate soil layer and the drainage layer. The main configurations of a green roof as following. The first one is extensive green roof, following by semi-intensive, and finally scenario is intensive green roof. Thermal properties of a green roof as following. The extensive roof thermal conductivity is 1.7, while the U value of semi-intensive is 0.38. The intensive green roof U value is 0.21 watt per meter square Kelvin. The total annual electricity for each green roof scenario as following. It's obviously that all scenarios achieve significant reduction in total annual energy consumption in comparing to the previous strategies. The extensive green roof is recording 113.2 megawatt per hour, following by semi-intensive green roof 93.7 megawatt per hour, while the highest reduction achieved by intensive green roof reached to 90.9 megawatt per hour. Overall, the final readings indicate that all strategies show various reduction in the total annual electricity consumption with slightly different ratios in compared to the base case. All scenarios achieved relative reduction in the total annual electricity consumption varies from 0.59% to the 31.84% comparing to the base case. The percentage of reduction in the total annual electricity consumption of the first strategy, following by the second strategy of the glazing properties, while the lowest reduction in the total annual electricity consumption percentage achieved by installing the green roof scenarios. Overall, the final readings summarize the optimal scenarios comparison in terms of reduction annual energy consumption. It's clearly noticed that the intensive green roof enhancing the reduction by achieving the highest percentage with 31.8 against the best case.
The functionality of the souk depends on both the comfort level inside and outside the shops, as people will walk between the different stores. Accordingly, we worked on improving the microclimate in the courtyard through introducing water features, shades, and trees. The base case and improved case were modeled in the infinite in 4 months: March, June, September, and December, and 3 timing at each month: 8 a.m., 1 p.m., and 4 p.m., similar to the IES selected date and timing. In each scenario, we studied wind, temperature, and relative humidity.